All right, diving in, this deep dive, it's going to be a little different. For you, our AI.Code.Cast listeners out there, we're taking on this coding challenge. It's called Word Break 2.
Yeah, it's a fun one. You know those times you're staring at code and it feels like you're trying to decode some secret message?
Oh, yeah, totally.
It's kind of like that. This problem, well, it's all about figuring out how to break a string of letters. You got to use words from a dictionary.
So, like, you give me a jumble of letters,
Yeah,
and I have to find actual words in there.
exactly. But, and here's the kicker, you got to find all the possible ways to break it up using those dictionary words.
Whoa, all the ways.
Yeah.
So it's not enough to just find one solution. Man, as an AI.Code.Cast listener, I'm already intrigued. Where do we even start with something like this?
Well, think about how we naturally solve word puzzles. Like, you see a string and your brain starts picking out familiar words.
Yeah, you kind of scan it, see if anything jumps out at you. But that feels kind of random, doesn't it? Like, isn't there a more, I don't know, systematic way to approach this?
There totally is. But that instinct you mentioned, that's actually pretty close to what we call a brute force approach in coding. Basically, you try every single combination of letters.
Every single one. Wouldn't that take forever, especially if the string is super long?
It definitely could, especially if you've got a massive dictionary, too. That's the problem with brute force. It works, but it gets crazy slow as things get bigger.
So brute force is out. What are our other options? I've heard these terms thrown around, like dynamic programming and I think even Trie. Are those going to be our heroes here?
They just might be. Dynamic programming and tries, they're like our problem-solving power-ups. But before we get into those, let's talk about some of the tricky parts of this challenge.
Oh, good point. Because I can already imagine myself getting tripped up, like finding one solution and thinking I'm done.
That's a common one. You got to remember, there might be multiple ways to break that string up. It's easy to miss some if you're not careful.
So we need a way to be thorough, but also efficient.
Exactly, and that's where dynamic programming comes in. It's all about breaking down a big problem into smaller, manageable chunks. You solve those little pieces, and then bam, you can put them all together to solve the whole thing.
Okay, I'm starting to see how that would be more organized than just like randomly trying combinations. But there's memorization and there's tabulation.
Ah, yes. Two flavors of dynamic programming. They both use this idea of breaking down problems, but they do it a bit differently. Think of memorization like keeping a notebook of clues.
Ooh, like a detective. So as you solve a part of the problem, you jot down the answer, and if you see that same part again, you don't have to redo all the work.
Exactly. It's all about saving time and effort.
Okay, I like that. Makes sense. So what about tabulation?
Tabulation is more like, building a house brick by brick.
Ooh, I like that analogy.
You're systematically building up a structure.
Hmm.
Each brick, represents a piece of the solution. You can't put up the roof until you've built the walls.
Okay, I'm starting to see the difference here. Memorization is like having our detective's notebook, and tabulation is like having the blueprints for our house. But how do we actually apply all of this to WordBreak 2? Like, can we get a little more concrete here?
Of course. Let's dive into some pseudocode.
Yes. Let's see how this works in practice.
Welcome back. Ready to see this stuff in action?
Oh, absolutely. As an AI.Code.Cast listener, I always got to see the code, right? Start with memorization. Feels kind of like the way I'd naturally try to solve this.
Okay, cool. So let's take that cat, sand, dog example and say our dictionary's got like cat, cats, and sand, dog in it. With memorization, we have this function. Let's call it a word break memo.
Word break memo. Got it.
And it takes a starting position as input. So word break memo 0 would mean we're starting at the very beginning of that string.
Right, makes sense. So what happens next?
First thing, gotta check if we've already solved this part. We'd need some way to remember, right? Like a dictionary or an array, something to keep track of those results. Let's say we haven't seen this part before, so we start going through possible word lengths.
So we check C, then K, then cat. Oh, cat. That's in our dictionary.
Boom, we found a valid word. Now we gotta call our word break memo function again, but this time on the rest of the string, that sand dog part, starting at position 3.
So it's like we're saying, okay, cat works. Now let's see about the rest of it. And
Yeah,
because this is memorization, we're going to write down what we find for sand dog in case we need it later.
You got it. Now, let's pretend those recursive calls, they eventually figure out that whole sand dog part and give us back a list of valid breaks.
Let's say they give us back sand dog and sand dog.
Nice. So now we take our cat and add it to those. We get cat sand dog and cat sand dog. We store those in our memorization table for position 0, and bam, we return them.
I'm digging this memorization thing. Break it down, remember what you find, and build it back up. Pretty neat. What about tabulation? How does that structured approach handle this same example?
Okay, so with tabulation, we build this table, call it DP. Each cell in that table, DPI, represents a starting point in the string. And each cell, well, it's going to hold a list of all the good breaks starting at that index.
So DP0, that would hold all the valid ways to break up the whole cat sand dog.
Exactly. We start off setting everything to empty lists, except for the last cell, DP9. Why? Because that last cell, it represents that G, the last letter. And since dog is a good word, we put dog in there.
Okay, so we're starting at the end and working our way backward. Why do we do it that way?
Ah, good question. Because by doing it backward, when we're looking at a spot, we already know the answers for everything that comes after it. It's like that brick by brick thing. You got to build the foundation first.
Right, got to have those walls before the roof. Makes sense. So
Okay.
what happens next?
We move to DP8. We check out the substring starting there. Og and dog. Og, nope, not a word. But dog, we know that's good. We saw it in DP9. So we add dog to DP8.
So we're basically using the answers we've already figured out to help us solve the earlier parts.
Exactly. Now, fast forward. Let's say we get to DP5. We check substrings starting there and find and, good word. Now we peek at DP8, which we know has dog in it. So we combine them and dog and add that to DP5.
I'm really starting to see how this table gets filled up with all the right answers step by step.
And by the time we reach DP0, boom, we've got all the valid word breaks for that whole cat, sand, dog string.
This tabulation thing is so clear. Now, I'm super curious about that try. Is that where it comes in?
It is. The try is going to make everything super fast. Remember, it's like a dictionary, but specifically for prefixes.
So every path from the top of our try, that represents a prefix of a word in our dictionary.
Gotcha. Precisely. Now, think back to our tabulation process. We're at, say, index 4, that S in sand. Instead of looking through our whole dictionary to see if words start with S, then sa, san, and so on, we use our try.
We just follow that path. S, saw, sand, sand. Boom, we hit a word.
And it's super fast, especially if you've got a huge dictionary.
Makes sense. Way better than checking each word over and over again.
Right. Now, we look at DP8, which we know has those valid breaks starting with dog. Since we know sand is good, we combine it with those, get sand dog, and add that to DP4.
This is amazing. The try really speeds things up, huh?
Oh, yeah, it's a powerful combo. And you know what? You can use that same try trick with memoization, too. Instead of searching the whole dictionary every time, you zoom in with the try.
Feels like we've cracked the code here. Backtracking, memoization, tabulation, and now the try. But as an AI.Code.Cast listener, I always got to ask about the trade-offs. What are the pros and cons of each approach?
Great point. There's no one perfect solution for everything, right? Each approach has its strengths and weaknesses. Before we get into that, though, let's take a breath, think about everything we've learned so far. When we come back, we'll wrap things up and help you choose the right tool for the job.
All right, back for the final round. AI.Code.Cast crew, we've really gone deep on this word break 2 problem. Feeling like a coding ninja over here.
Yeah, we've covered a lot of ground, but before we wrap up, let's, step back and think about how to actually use all this stuff. We've got all these tools, backtracking, memoization, tabulation, and that try optimization. But it's like, when do we use which one?
That's the big question, right?
Yeah.
As AI.Code.Cast listeners, we want to write code that's, smart and efficient. So how do we choose the right approach?
Well, let's start with backtracking. It's easy to understand, but it can get really slow, really fast. So if you're working with like a short string in a small dictionary, backtracking might be fine. But if things start getting bigger, you'll want to think about those other options.
So backtracking is good for small stuff, but not for those heavy-duty problems.
Yeah.
That's where dynamic programming shines, right?
Exactly. Memoization and tabulation, they're both dynamic programming techniques, and they can make things way faster. But there's a trade-off. They use more memory. We're storing all those solutions, and that can add up, especially if the problem's complex.
Right, so it's a balance. We're saving time, but we're using more space.
Mhm.
Classic coding dilemma. So how do we decide between memoization and tabulation? They both seem pretty awesome.
They are both powerful. Sometimes it comes down to like personal preference or what the specific problem looks like. Memoization, it can be a little easier to code sometimes because it often just follows the natural way the problem breaks down. Tabulation, it's more structured, step by step. And sometimes it can be even more efficient, especially if you need to get to those solutions in a particular order.
So memoization is more like go with the flow, and tabulation is like follow the plan. And then there's the try, our super fast word finder. When is that optimization really worth it?
Anytime you have a giant dictionary or if you're doing a ton of word lookups, The try is your best friend. It makes those lookups lightning fast, which can really speed up the whole solution.
It's like having a shortcut to find exactly what you need. No more searching through the whole dictionary. I'm really starting to see how all these pieces fit together. It's like we've got this whole toolbox for word break 2 now.
That's it. And the trick is knowing which tool to use for each job. Sometimes you need something quick and simple. Sometimes you need something more powerful. You AI.Code.Cast folks out there, you're ready to tackle this problem now.
This has been awesome. We've gone from like basic backtracking all the way to try optimization. Feeling pretty confident about breaking up any string now.
That's the attitude. But the learning never stops. There are always new algorithms to discover, new ways to optimize.
I love that. So AI Codecast listeners, keep coding, keep exploring, and keep pushing those algorithmic boundaries. Who knows what you'll come up with.
And remember, you're not alone. There's a whole community of coders out there. Share your knowledge, ask questions, help each other out.
This has been The Deep Dive. Signing off. Keep those algorithms humming.